Well, welcome everybody to our Thursday evening Zoom sponsored by GLREA. And I'm John Sarver, as you can see on the box there. First thing I need to do is to thank our sponsors, the State Department of Environment, Great Lakes and Energy, Eagle, Homeland Solar, Harvest Solar, Sri Energy, and Sumter Solar. And, there's been a lot of interest and questions about batteries. So I was real glad that Lee Andre had suggested that Ed Shaffer come and talk to us tonight. Ed is the CEO and founder of Advanced Battery Concepts. And so I think a company that's headquartered in Clare, Michigan, a Michigan company, a battery company. And so I think he's going to be able to kind of bring us up to date on certainly what his company's doing and probably what's happening in the overall market. So with that, Ed, go ahead and the other thing I'll just mention is please mute yourself while Ed is doing his presentation because we'll have time later for you to ask questions. Go ahead, Ed.
Great. Thank you, Lee, and really happy to be here this evening with everybody. Thank you for your time. So I'm Ed Shaffer. I'm the CEO and founder, my favorite title, of Advanced Battery Concepts. And we're going to tell our story today. But at a higher level, what we've done here at ABC is we just made the traditional lead battery better. And we've made it competitive with lithium, specifically lithium iron phosphate, for energy storage applications. By way of background, I used to work at Dow Chemical for 20 years. I had a variety of roles there. I did a lot of new business development for Dow, which got me into the energy space. I'm a PhD from MIT, and that and $1.50 buy me a cup of coffee. I actually think it's $2.50 now. Buy me a cup of coffee. I was always fascinated with the energy space, and in 2007, I was hired by a company in Wales, and they said, "Hey, we've got a better way to make a lead battery, and it's called bipolar architecture." And in the world today, just so everybody knows, 99% of all large format rechargeable batteries are either lead or lithium. So if you guys are interested in the space, I'm sure every week, like I see, there's some new scientist who came up with a new battery chemistry or something, a better way. This technology could revolutionize. This technology may revolutionize. Great. 99% of all batteries today are lead or lithium. And there's a reason for that. Because to support a battery industry, you need global mining. You need global refining. You need global supply chains. You need bankability. And these chemistries that are new have a long way to go and recycling. And the lithium guys are struggling with that. So when I had the opportunity to make a better battery, and I'm pretty good at lithium, we all love lithium, but to make a better lead battery really is meaningful to the world. We, in America, we get lost because we have Teslas, and those are great cars, but a lot of my friends, rightfully, call them driveway jewelry. And that's pretty good for Americans. But if you're a e-rickshaw driver in Mumbai, Tesla is nothing but a dream. So when we talk about electrical vehicles, the vast majority, over 70% of EVs use lead batteries because they're e-bikes or e-rickshaws or tuk-tuk trucks, things we don't see in America, but they're there. So when I was introduced to the idea of making a better lead battery, it was meaningful to me, to the point where I resigned my job and prayed with my wife. We're a blended family. We had 5 kids. We had 1 in college and 4 in high school. And I said, I can do this. We can make a better world. And I cashed in my 401k and started in my garage. And here we are today, sharing our story. And it's a quintessential American story. Founder in a garage, right? We all love it. So I'm really happy to share what we have and what we offer. And you're going to hear a new word today. The joy of being a founder is you get to make up words. And so the word I made up was green seal technology. And green seal technology is just the technology suite we use to build a better lead battery. And the result of that is affordable energy storage, safe energy storage, and sustainable energy storage. We all understand that most of our customers in a variety of applications are driven first and foremost by ROI. I'm an industrial scientist and I love ROI. I do not sell product at a loss, just FYI. And so we're focused today mostly on behind the meter projects. Um, we're a small company, and so those give us great opportunity to demonstrate our technology. But we're coming in competitive with lithium iron phosphate. I'm sure that everybody understands that 99% of all lithium iron phosphate cells today in the world are produced in China. 99%. So today's ESS solutions that are being offered to you by a variety of companies rely on lithium iron phosphate cells out of China. It's the thing. We don't. So we're competitive economically with them. We have the same long life as them. We're offering a 10-year warranty, mostly through energy throughput, so daily cycling, 100% DOD. Our technology is designed to not have capacity fade. It's a different thing. So in the lithium world, you're used to augmentation, right? Or some sort of capacity fade. Our batteries are designed to give you 100% every day for those 10 years. And of course, we qualify today for the 40% ITC with no tariffs because we're predominantly USA content, right? We're made right here in Clare, Michigan. The thing that I really like about it, well, no, I'm going to say that sustainability is better, but safety. On our board of directors is a gentleman named Bob Gallion. Bob was chief engineer of the EV1 project at GM. He was CTO of CATL, the largest lithium battery company. And Bob has the 5 golden rules of batteries. And rule number 1 is safety. And I love that about our batteries. We're aqueous, non-flammable electrolyte chemistry. There's not enough energy in our battery to catch our battery on fire. And even better, let's say our batteries are on fire from an external source. They have a fusing mechanism designed inside of them that, and we'll talk about the science behind that cause them to stop being a battery. It opens, it fuses open. Then the last component is sustainable. We are fully recyclable. The lead that we use in our batteries was probably mined in the 1930s. It just gets used over and over again. So we use recycled lead. We use a lot of recycled plastic, domestically sourced materials, all made right here in the United States. A lot of advantages of our technology. So today we have 3 product lines focused on different markets. So we have a residential energy storage system we call HEES, Home Electrical Energy Storage. We have a SEES product, Commercial Electrical Energy Storage, and then a BOXB product, which stands for Box of Bipolar Energy, for industrial and utility scale projects. All of these products use the same battery module. They use the same battery. We just connect them up in different ways to give you the power and energy that you require for the projects that you have. And then we've learned, and I love this space a lot. I'm learning a lot. The applications are diverse. It's not one size fits all. Every customer has a little bit of different power or energy requirements, voltage requirements. And so our systems are pretty flexible to meet the needs of optimizing for what the customer has today. And so uh, our products, they can range. Our batteries are 48 volt. This is one of our batteries right here. It's a 48-volt monoblock. And so we just stack these up. So anything like 288 or 384, 1152 volts, we can do more and more. Um, so our home unit is really designed from 6 to 48 kilowatt hours. We're offering a 10-year warranty with daily cycling, 100% DoD. What we really offer is energy throughput, um, or a 10-year calendar life. We have one advantage is that, again, as I said, there's no capacity fade. So when we say 48 kilowatt hours or 24 kilowatt hours, that's for the life of the battery, every day, all day. And that ranges from minus 20C to plus 55C with no derating. You get below minus 20C, we start derating a bit, but you can still use it. And so the good news is at the end of life, there's still value because they're lead batteries. So probably a lot of you are familiar with core exchange. It's the same thing here. We're still wanting that battery back because we're going to use those materials and recycle them and build the next battery. And then our commercial energy storage, again, it ranges from 48 to 384 kilowatt hours, 10 years, no capacity fade. Again, collect at end of life and fully recycled. We do have one product that's a stackable version of the commercial unit, the C's unit, because a lot of people, they're putting us in pole barns, and so they like space, so we can stack our units on top of each other to help meet the needs of space requirements for some projects. And then the box B comes in either a 10-foot or 20-foot container. You can put them in parallel. You can build them up, so you can build 5 gigawatt hours or 5 megawatt hours, sorry, of systems. And again, everything that we said before. So pretty straightforward product. And so, but I do want to talk a little bit about ABC. So in 2009, we started the company. It was focused on making batteries that achieve superior performance, specifically around lead chemistry. Again, lead chemistry is in every major economy of the world. If you're in South Africa, India, China, Japan, Korea, England, France, Brazil, every major country has lead recycling in their infrastructure, and they can all make lead batteries. And so we're really focused on how do we make a better lead battery. And that's when we came up with our Green Seal bipolar technology. And I'm going to explain the word bipolar. And for those of you who like brand challenges, I have to overcome bipolar lead acid battery in my branding. So I feel good about Green Seal. The rest of it is a bit of a challenge. More importantly, we had to use global supply chains with non-conflict materials. I think cobalt's going away, and that's because cobalt is mostly mined by 8-year-olds in the Congo. So that's a challenge. But every country, understands that they need to be able to sustain energy. And so they need to have that domestically available material to do that. And of course, it's got to be scalable. We're at megawatt hours, you need to be at gigawatt hours. And when you go through our technology, you'll see that we are scalable. So right now we have a production facility here in Clare, Michigan. That's a picture of it. And it is the future site for a gigawatt hour per year facility that we can build here. So Green Seal technology is a bipolar AGM lead acid battery. So AGM is also known as VRLA. It's an absorptive glass mat separator that causes recombination electrochemistry stuff. And what we've invented is not new electrochemistry. We've just invented a better way to make the lead battery. So Green Seal covers both the design and manufacturing engineering required to make this battery. We have 80, actually I learned today we have 86 globally patents issued. We have over 45 trade secrets, but more importantly, it uses commonly available materials. Critical to the lead battery industry is recyclability. Lead batteries are recycled at over 98, 99% today. There's no other commodity in the human endeavor that comes close to the recyclability of lead. And it's because secondary lead, recycled lead, turns out to cost exactly the same amount as primary lead. So from an economic viewpoint, there's no disadvantage to buying secondary lead versus primary lead. The same is not true for lithium. Secondary lithium is not a thing. There's a lot of work on trying to make recycled lithium. Most people are just harvesting the nickel, the cobalt, the copper, the aluminum, but the lead is, the lithium is very difficult to recover and economically versus primary lithium. So we also improve current density. So the architecture, and I wish I had invented it, it was invented in 1924 by a gentleman named Peter Kapitsa, who went on to win a Nobel Prize. But it really causes uniform current density across the battery. And as a result, you reduce the amount of active material required to give you so many amp hours, right? It eliminates hotspots and failures and increases power density. Does the terminal, I'm seeing a question here, like Larry, will it stay constant? No. So the terminal voltage, so when you're measuring the voltage, we are not constant like lithium iron phosphate. So voltage of an aqueous system is described by the Nernst equation. It's a thermodynamic equation that is based on the activity coefficient of the electrolyte. So for us, it's based on the concentration of the acid. So when you're discharging a lead battery, you're changing the sulfate to sulfuric acid, and you're converting it to lead sulfate. So as a result, the concentration comes down. So we have a very linear range of voltage through the discharge curve, which is great because it gives me great insight into the state of charge in the battery. So understanding the state of charge and also the state of health is all monitored through voltage of the battery, primarily in rest conditions, but also through the discharge. The bipolar construction is also way simpler. I mean, we basically make a bipolar electrode, we pot active material on either side, negative and positive, and then we just stack these things up. So it's a pick and place operation that we then overmold with plastic. So it's reduces the bill of material and reduces capital cost. And the result of it is just a better lead battery. It's longer cycle life, lower production costs. I'll just give you some data. Here's numbers. To build a lithium iron phosphate gigafactory in America today is going to cost you about $125 million. To build a gigafactory of traditional lead batteries is going to cost you about $75 million. To build a gigafactory of green seal batteries is going to cost you $50 million. We're just lower, we have less unit operations, less steps, less handling. My background, my PhD is in plastics, polymer science. So if you ask a polymer material scientist to invent a battery, you're going to get a lot of plastic. So what you're looking at here is a cross section of our battery, and the red material is the positive, the gray material is the negative, and the dusty white material is the separator. So you see, we just stack these cells, and then there's a black line with a little bit of lead foil on each side. That's the bipolar electrode, and that is this, and that conducts electricity from one cell to the next cell. So you have ions transferring charge in the cell, then you have electrons transferring charge into the next cell. So you just build up voltage. So 2, 4, 6, 8, 10, 12, and this is a 48-volt battery. You'll see some features in there. So over here, we injection mold plastic tie rods through these holes we call via locks, and that's what holds the battery together. And then we have something we call a sure fill channel. And you see each of these little holes is how we bring acid into each of these cells. And that's technology that's unique to us. So let's see, I'm looking at some questions here I'm going to try to answer. So one question is the cell 2.2 volts per cell? Yes, it is in actuality at OCV, but nominally everybody uses 2 volts per cell through the discharge curve to calculate kilowatt hours, which is what we do. And then we are 20% cost. Lithium iron phosphate is pretty cheap. China's very competitive. So on kilowatt hours, so we're competitive with them on production cost. But and we can do better. We're going to talk about that here a little bit. So the main thing we do is we improve manufacturing quality. And that's really what we focus on. So our bipolar design eliminates the ways that traditional lead batteries fail. Active material shedding, plate growth, and acid stratification. Those failure modes are just not available in the bipolar construction. And we compare ourselves to our colleagues in the lead industry, and we are setting uniformity and reproducibility standards that are not achievable in the lead. We're very similar to the lithium guys. So we're running 100 quality checks through the process. We have full traceability, but the way we control everything is weight of the active materials, weight of the acid is the same in the technology. And then, as we said, we extend the cycle life. The cycle life is, it's the good and the bad of being a battery developer. And I wish my investors would give me 15 years to start a research institute to develop the perfect battery. But you got to do what you got to do to prove that the battery's working. So we've been running 3-year demonstrations on our batteries here at AVC. And then we look at trends and project life on that because we got to get into the business. So the key is we understand the science behind our failure modes. So we've done a lot of work on how we fail, and I'll just share with you. Our failure mode is corrosion of the positive lead foil metal that we use as the current collector. And so eventually this lead metal on the positive will turn to lead dioxide. And so that is our failure mode. And we know the corrosion rate, so we designed the thickness of the foil to give us the lives we need. And so this is an example of what you, the customer, would see. This is 3 years, daily cycling at the 4-hour rate, and every day you see the same amount of energy being delivered to your batteries. Question online is, aren't all batteries bipolar? No. No. Lead batteries today are monopolar construction where they have positive and negative active metal grids that are stacked up. Lithium batteries are just cells or pouches. They're not bipolar, they're singles. There are some bipolar nickel metal hydride batteries, rare. There's a couple. So lithium batteries are just single cells and not multiple cells. And in fact, you can't make a bipolar lithium battery because of voltage control, because it's non-aqueous electrochemistry. You could do other electrochemistries bipolar. Flow batteries are bipolar, and fuel cells are bipolar architecture. Let's see. All right. So, and paramount to us is safety. We are the first ever bipolar lead battery to receive UL 1973 certification. So we're pretty proud of that. If you're familiar with the industry, there's a lot of accommodations for lead because lead is safe. The NFPA put out a report canvassing failures of lead batteries over 25 years, and I think they found a couple of dozen failures. And I mean, they're very safe. They're intrinsically safe. There's not enough energy in this battery to catch this battery on fire. Plus, we have the fusing mechanism that I described that is core to our green seal technology. Another question online is nickel iron batteries. Have we looked at those? Yeah, we did. We did some studies, and nickel zinc as well. We looked at nickel zinc on our technology advisory board. We had a nickel zinc guy. Bipolar nickel zinc's got a lot of attractiveness, but the problem with both of those is nickel. Nickel is very expensive and hard to refine in battery grade. And again, back to that global infrastructure around harvesting and using nickel, it's not as well developed as lead. And then nickel iron. The problem with nickel iron is it runs forever if you run it forever, but if you stop, you're dead because of dendritic growth of iron. So that's one of the challenges there. But it is intriguing. And I would love to start the Ed Schaefer Institute of Science, looking for sponsors to go and explore alternative chemistries from lead. But remember, lead is a globally developed chemistry. This technology drops into existing lead battery plants. So ramp rate to scale is pretty high with lead. So we're a young company. I mean, like most of our history has been developing all of the engineering and science around the things we do. But we are in the business today. We've had residential energy storage systems in a beta program for over 2 years, learning good, bad, the ugly. I'm going to share, we've got projects with the National Park Service, an off-grid project here in Michigan on the Manitou Islands. We've been working with a high power DC to DC EV charger guys, and they're ready to scale up. They've got projects for in the state of Washington along I-5 that we're working with. And we've done some work with the Department of Defense to show how energy storage could be used in a forward operating base using our batteries as well. So we're pretty excited. The National Park Service put out competitive bids for an off-grid project on the Manitou Islands here in Michigan, in Lake Michigan. And these islands, they need their own power. So this is a combination of solar and generator power with our batteries to deliver the power requirements to the island. We were selected mostly because of safety. What the National Park Service doesn't want to hear is the word fire. And this island is turned off in the winter. So your batteries are on stand over the winter. Cold temperature stand is extremely dangerous for lithium batteries. Do not store your batteries outside in a garage in the winter. Not advisable. And so we've got the purchase order and we're building the systems right now. And we'll be installing the North Island here in September. So we're pretty excited about this project. But we're not done. You know, our technology is young, and we've already started developing Gen 2 technology we call Evergreen Seal. And it's really focused on large utility scale projects. It's offering 15 years of daily cycling with zero capacity fade over life. And it's competitive installation costs with foreign sourced LFP. And the key about this battery that I'm very excited about, it's about the sustainability. It's the first battery designed to be disassembled at the end of life. So instead of grinding it up and floating the plastic this way, this thing is disassembled, which gives us direct access to the active materials, the separator, and the plastic components. And as a result, we can reuse those to build lower cost replacement batteries or secondary batteries. And ABC has developed a proprietary process for recycling all of the lead waste hydrometallurgically with zero waste. And that goes right into making the next set of lead monoxide that we need to build the next battery. So we're pretty excited about the ability for us to continue to advance that. So it's all about installation cost in the utility world. So today our green seal technology for a 10-year battery, looking at the batteries, the balance of systems, the conversion, the inverters, and the EPC costs, we're at about 414 kilowatt hour installed at the gigafactory scale. When we go to Evergreen Seal for 15 years, we're at $250 a kilowatt hour installed. Now we're not there today, but we have clear engineering plans to get us there, which is good news for all of us, because at the end of the day, it's about the levelized cost of stored electricity. So today we're pretty competitive with our green seal technology. We're running about 12 to 13 cents a kilowatt hour over the 10-year life for the cost. The Evergreen Seal gets us just a little bit north of 5. But if you look at the recycling, recovering and replacing on a 30-year battery, you're now at 4 cents a kilowatt hour. 4 cents a kilowatt hour of storage combined with $1 a kilowatt solar beats out combined gas cycle turbine natural gas power plants on price. That's a big, big, big thing. So we're here today, but we have a plan to get there tomorrow. We're pretty excited about that. And we're hoping to build some momentum to attract capital to continue that engineering. So a question on the field about the aqueous electrolyte. It is sulfuric acid, it is acidic. And the question is, well, what about leakage? And is that the thing? So that, I love the question because that was the whole shtick. There's something called edge seal rupture, and there's no leakage. That's not allowed. There's no way for the lead to leak out of this battery the way it's built and designed. So where are we today? We have assets. And we're leveraging those assets to build and sell products. So we have our 3 product lines, and what we're doing is showing both the manufacturing and technology readiness to reduce risk of adoption for our partners, right? And we're open to work. So if you guys know anybody, we really want to build a network of folks who understand applications, markets, and channels that can start offering our products as an alternative to Chinese sourced lithium batteries. And we value those relationships, and we're very flexible on how we work with people. And, we're willing to work with folks if they want it white label or specified. We're absolutely flexible on how we work with folks. We like focusing on the engineering and technology. You probably got that sense from Dr. Shaffer here. But at the end, it's about making a business. I have shareholders. We want shareholder return. And so we're really looking at working with folks, putting systems in the field, building that bankability data, showing a path to improved contribution and sizable return for our shareholders. So that's our story at Advanced Battery Concepts. And I see a couple extra questions here. One question is about off-gassing of hydrogen. And so it's true. Every time you recharge a lead battery, you're above the electrolysis potential of water. So you generate a little bit of hydrogen and a little bit of oxygen. And so the good news with our batteries is charge acceptance is very high, so our charging voltages are lower. So the amount of hydrogen and oxygen generated are very low. And so they do off gas and they just vent in the air, and we're well below the limits of safety. I think 4% is the safe limit of hydrogen. In internal, we target 1.5% or lower. There's another question around weight compared to lithium. And I'm not going to be shy. Weight has never been my friend. Ed Shaffer is a big guy, and our batteries are big guys. So they do weigh more. We're probably 3 times heavier than lithium batteries. And in the energy storage world, what I've heard from installers is, okay, I'll bring a bigger fork truck, or build a bigger lift crane. Not a problem. Nobody cares about weight. Nobody cares. Now, if you're driving a Tesla, everybody cares. But for energy storage, we have not had anything. And now we're also volumetrically a little bit bigger, but under the guidance of a lot of the new standards with UL 9540, lithium batteries are having to be spaced 10 feet now from each other to prevent fires jumping from one battery to the next. So although we are not as energy dense, we can be packed closer together. Another good question from the audience is around cooling. So we use convective air. So in the lead world, like all batteries, temperature's a thing, right? But for us, we're nowhere near as sensitive to temperature as lithium batteries. Now, as I said, our failure mode is corrosion of the lead foil. And the warmer it is, the faster it corrodes. So all of our corrosion rates are designed at 35 C ambient temperature. The hottest city in America is Phoenix, which is 28 degrees C. New York is 17 C. So we've got a factor of safety in there, but it's really only about the corrosion rate. Now in the lithium world, they'll share with you our cycle life at 20 C was 4,000 cycles. But at 25 C, it might be 2,000 cycles. At 30 C, it's 1,000 cycles. So their life sensitivity to temperature is much higher. So they really are forced to deal with air conditioning systems that we don't have to deal with in the lead world. And then in another good question, in normal service, do these batteries need to be equalized like lead batteries? The answer is yes. So the way we run these batteries is our battery management system is monitoring the voltages of all the battery packs that are in parallel. And every once in a while, we have to do an equalization charge to bring them all up. It's one of the great advantages, in my opinion, of aqueous chemistries, because you can overcharge good batteries and not hurt them and let the bad batteries catch back up. So there is equalization. We're learning more about that, like how often do we need to do that? That's why it's so important for us to get product in the field. We learned a lot from the 2-year studies, but we're pretty excited about that. Another question is, how do your battery costs compare to LG's LFP batteries from Holland, Michigan? So I have not gotten price indications from LG. They are building a 16.5 gigawatt hour facility in Holland. It's pretty big. I would say right now we're probably a little thick on their versus their cost because they're at 16.5 gigawatt hours, and I am not. But if I was at 16.5 gigawatt hours, I would readily beat their price. I think we are still competitive though, because it's I don't know where their pricing is going to end up. They've given some indications at cell level, but I don't know where they're going to end up on the energy storage level. And then also, I don't know where they're sourcing their lithium from, because it's not America. I mean, they just announced a deal with First Phosphate, but that whole infrastructure has got a long way to go there. So we'll see. I've actually enjoyed competing against LG in the marketplace. They put out a lot of NMC product, and that was very unsafe, and they did not do well. And that really has done a good job promoting our opportunity in the energy storage sectors.
Ed, why don't you stop the screen sharing and we'll take some more questions.
Sure. Awesome.
It's a little easier to see people if they raise a virtual hand and want to actually ask a question. And, if you want to, put your question in the chat. Looks like Lee is watering, question mark.
No watering. A great question. Lead has a lot of history. So these are completely sealed batteries that require zero watering.
Other questions,
Yeah,
again,
so where does the hydrogen come from then?
So the hydrogen is from water. So Lee, I know how much dry out, I know how much water is leaving per cycle. So I design the charging algorithms and how much water is in there to start with. So right now this battery is designed with 22 years of dry out life. So the corrosion is my failure mode, not the dry out.
Understood. I do have another question then. In the other chemistries, you frequently see charging rates and discharging rates. So you can charge very fast when you're in the mid range of the depth
Yep.
of charge, and then it tapers off as you start to get above 80 or 90%.
Yeah.
So do you have I'm surprised you don't present a curve that looks like that for your battery.
Oh, it is. It is that way, for sure, Lee. Now what we can do is we can work in the partial state of charge regime for a while, and we've got data here at ABC that shows that, where let's say you're doing a constant power charge and discharge, right? Because in the utility scale, if they say they have 50 megawatts, they have 50 megawatts for both charge and discharge, right? So we'll run 50 megawatts, maybe a 4-hour discharge both ways. But once a week, you got to come back in and top it off because you're energetically balanced, but you're coulombically imbalanced. So I said that the wrong way. You're coulombically balanced, but you're energetically imbalanced. So you've got to just put more energy into it every once in a while. So, depends on the system we're working with, Lee. We're developing our own BMS system so that we can optimize that charging algorithm. But most traditional inverters have traditional lead battery charging algorithms, which would be akin to what you're used to. Charge it fast, let it soak, let the voltage or let the current drop a constant voltage, and then it's done. In the markets that we're dealing with, 10-hour recharge times isn't really hurting anybody's feelings because they're charging them up overnight, late at night. But we can accept faster charge for sure. The problem is almost everybody I've been dealing with, Lee, is that their discharge power is the same as their recharge power. So if you could you know, for example, I've got batteries on cycle where I'm doing 100-hour discharge. Right. I love, if anybody's got 100-hour discharge energy storage application, I'd love to talk to you. So we discharge it very slowly and then I recharge it in 5 or 6 hours. Right. So it's all about balancing that power. And most systems are designed that your power is your power. So therefore you just have to charge it longer with constant power to get to where you need to be.
And the round trip, I didn't hear you mention the round trip efficiency.
Yeah, I mean, right now we're probably with standard charging algorithms like constant current, constant voltage, we're about 87% RTE, but we're developing BMS and we've been able to get as high as 93% DC to DC round trip efficiency. So it really depends on the charger, to be honest.
Phil, you want to go ahead and ask a question?
Sure. I actually had a couple of questions. One is on your website, you have pictures of like a home unit, and I was just wondering how heavy are those?
Yeah, they're heavy, Phil. So we offer a couple of different products. The ones you probably saw are what we call our He's Light. So those are each of those containers is 6 kilowatt hours, and you can build 2 of them. And those were designed to be assembled on site. So the electrician would bring down each battery, put them into the container, and hook them up.
So if I had a basement application, that would be assembled in my basement?
Yeah, that's right. So it was designed. When I first started this, Phil, look, I'm a Michigan guy, right? And I'm a clear Michigan guy. Like, I mean, we got basements and, crawl spaces and stuff like that. So my vision was always designing it to be assembled on site, which we still can do, Phil. But we do have larger systems that are designed to be fork or, like a little lift truck to bring onto site. Our He's 24 kilowatt hour system, I might be a little bit off, but it's around 1,800 pounds, somewhere around there. Our 48 kilowatt hour C system is 3,700 pounds. So we're heavy, but we could design systems to be assembled on site. I always loved that vision for most homeowners.
Right. I have a second question. On your website, I noticed you had equipment, Epsom equipment. Is that 3D printing that you're doing or no?
Oh, no, those were the Epson robots, scarabs for pick and place, for stacking and building our electrodes.
So is the plastic in those units recyclable, or is it just?
Oh, for sure. Absolutely. So right now we're using fire retardant grade ABS. That's pretty common, but we also use polypropylene. We're using all of our regrind products and putting it back into the systems for various components that we use. So we can use recycled plastics as well.
Okay, thank you.
In the chat room, we've got a question about, are you doing most of your business in Michigan or out of state?
Yeah, right now we're in the state, of course, because we're Michiganders, but we're very open to other states. I think, what we're learning is every state has different requirements. I mean, PJM, you guys probably just saw this. I mean, they just slammed their customers on peak power demand charges. I mean, their peak power demand charges went up 5 to 7x. Oh, you got a plant you're running in New Jersey or Pennsylvania or Maryland. Oh my God, your bills just went up, right? So there's some market opportunities there, but we're not out there. So we're certainly open to that. Yeah, and also, in Michigan, right, we're 24 cents a kilowatt hour. 24 cents. Bad for my home front, but good for the battery business, right? But if you're in South Carolina and you're at 8 or 9 cents a kilowatt hour, well, I don't need your battery. It's okay. I'm okay, right? So we'd love to get out of the state.
Yeah, Clifton asks in the chat, some of your specs say 100% DOD for normal cycling. Is this correct? And how does it not damage the battery?
Okay, great. All right. I made a decision because there's, you all know the story, right? Liars, damn liars, and battery suppliers, right? So I said, look, when we say the battery has this much capacity, I mean that's 100% capacity that they cycle at, and that's what they pay for. So when we give you a 48 kilowatt hour system, we've already designed in all of the buffer needed to make sure the battery lasts as long. I've done that math. You don't need to do that math. So we're selling you 48 kilowatt hours at this price that will cycle 100% depth of discharge over 3,700 times. We've designed that in, right? Now, the battery actually has more energy, but I don't let you access the energy because I want the battery to last 10 years, right? There's another joke in the industry: batteries don't die, they're murdered. Uh, so, uh, so that I try to prevent people from murdering our batteries by controlling the charging algorithms and controlling the discharge algorithms.
Hey, Lee asks, you looking for new shareholders?
Always. We have a vehicle open. We're very open to investors, and happy to send our CFO your way to talk to you about our current offering.
Sounds like an opportunity for some folks.
Yeah.
Marcia, go ahead. You're muted though. Go ahead and unmute and ask. There you go.
Okay, thank you. That was fascinating. Of course, I don't know all the details of the science involved, but I have solar panels on my roof, 20, but I'm in a house that I only live in 6 months of the year.
Okay.
And so I've been told that the lithium batteries would not suit me because I leave the house, I drain the system and I let it freeze in the winter.
Great.
And so what about your batteries? Would they?
Yeah, Marcia, that's right on. That is a common and understandable concern with lithium batteries. And that's why we won the Manitou project. Our batteries can stand for 6 months. So stand just means you turned it off. It's just standing there. It's not doing anything. And it can stand for 6 months, and you come back, you do a boost charge, and away you go. The batteries are all good to go.
Well,
So,
my panels work all winter, of course.
oh, great. Then you can top off. You can every once in a while just do a little top off charge. Everybody's happy. But yeah, our batteries hold capacity quite well through the winter.
Okay, that's good to know.
Yeah.
John, go ahead with your question.
So, Ed, great presentation. So, with everything that's going on in the world,
Mm.
Trump's bill, the anti-China sentiment, supply chain challenges, what do you see in the next, let's just talk the next 5 years in terms of the evolution of the battery industry? You make a very persuasive case that your product is going to be competitive for a number of very good reasons. But I'm also interested in what other people are. I mean, you follow this stuff. You're in
Oh,
the.
yeah. I'm in, I'm in it, John. And now, of course, I'm a founder, so I have a decided bias, right, John? So, but at the end of the day, I'm an industrial guy. I'm here to make money for shareholders. And if I didn't think we could make money, I would tell my shareholders, guys, it was a good run, but China won, right? I could say that. I don't see that happening. I look at our cost savings as we evolve the engineering suite of our technology, and I think we can beat lithium iron phosphate hands down, but I got to get there. Now, the question is, John, can I get there?
But what about cars, though?
Oh, no, cars were out. We don't do EVs. The hard part about building a better battery is everybody comes to you and says, well, I got a friend who does this with batteries, and I got this with batteries. And it's hard because now you're chasing squirrels, like squirrel, and we gotta go. Airplane batteries. Oh, airplane batteries, So we're very focused on energy storage. We know our space in the EV is limited in America. Now, having said that, John, we have licensing relationships with companies in India and China, East Europe, that could take this technology for low speed, low distance electric vehicles. And when we talk about EVs, we have a very American lens on EVs. I gotta tell you guys right now, 90% of the EVs in the world do not go faster than 35 miles an hour and do not go more than 35 miles a day. Because we always think of a Tesla, but the vast majority of EVs are electric bicycles, electric scooters, e-rickshaws, e-tuk-tuks, you know, those small little lead guys that are just putzing around Mumbai and Jaipur and all around the world.
Yeah, but Ed, BRO, I think the Chinese company, they're opening up factories in Europe. It's my
Yeah,
understanding.
there's BYD, I think it's who you're talking about.
Okay.
And BYD is huge. They're massive. Great company. CATL, another great big company. They are, but they're focused on the automotive BEV. And I'm John. So you ready for this? I want EVs to go like gangbusters because all of the lithium batteries will go to EVs. My problem right now, that 16.5 gigawatt hour LG plant, what did they say? They said, we're building this plant for cars. Oh, wait a minute. Cars aren't happening. We're switching. We're going to ESS. I want them to go back to cars, John. I want more EVs. So now, again, I'm an industrial guy. If you want EVs, you need charging infrastructure. The Department of Energy, I was always frustrated with them because they focused on range. They thought people have range anxiety. And the range of your electric vehicle is all directly related to the energy density of your battery, period. Right? So that's what's been driving America to look at 811 NMC and just, but no, that's not what it is. Range anxiety isn't how far I can go in my tank. It's where's the next gas station? That's range anxiety. And so we need charging infrastructure. It's a good deal for us because the best way to charge a battery is with a battery, right? So we're working with companies that are starting to think about integrating ESS into their charging to minimize their interconnect cost. So think about, you've got, like, I got guys who are talking about 400 kilowatt handles. So you got 10 400 kilowatt handles at a gas station, right? An EV charge station. Now you got 4 megawatts of peak power you got to supply to that. You've now got to go buy a 4 megawatt interconnect agreement with your utility company. It's costly and expensive because the utilities companies it's like, oh my God, we got to build a new substation. What you could do is you could put in a 400 kilowatt battery system with a 400 kilowatt tie to the grid because nobody's there at 2 a.m. So I've got all night to charge the battery. So I can reduce my interconnect. Instead of 4 megawatts, I can be 400 kilowatts, right? And it needs to be safe. Lithium's headwinds are safety and Chinese supply. Those are the two headwinds. LG is trying to fix that. There's other companies trying to fix the supply, but the safety issue is big. And in urban areas, it's going to be very difficult to have aggregated lithium energy storage. So it's a great market for us to be focused on because, again, nobody cares how heavy you are. You're just sitting there, right? You're just a big container, right? Nobody cares. So I want the EV market to come back, John. I'm not going to participate in it other than selling batteries for charging stations and then getting one of my competitors off the playing field. It's all good for me. So go buy EVs. Buy EVs, everybody.
And that's a good way to end. We're after 8 o'clock. Hey, Ed, thank you very much. This has been very interesting, informative, helpful, I think. Because
Yeah.
we're all kind of wondering about batteries and different chemistries and the roles that different batteries play in the kind of in our environment. So this has
Yeah.
been very helpful to kind of, I think, give us a better understanding of what the different choices are and the different applications. So thank you very
That's
much.
right. You're welcome. And John, feel free to share my email address. And if anybody has questions, happy to answer them via email.
Okay, super. Again, thanks. And thanks for everybody who's attended. And, we've recorded this. And so we'll, it'll be on our YouTube channel, GLREA YouTube channel. And everybody have a good evening and a good weekend. Take care, everybody.
Thank you all.